So, good afternoon, everybody. Welcome to today's webinar on energy conservation using ultrasound to improve your plant's energy efficiencies. Just a few housekeeping rules before we start. This webinar will be recorded. It will be up on our YouTube channel later on today. There are times for questions throughout the presentation. If you would like to ask a question, you can add it into the chat group and I will try my best to answer it as we go along. As you can imagine, we have a lot of people attending today, so if I don't answer your question, I will make a copy of all questions and make sure that I email you those in the future after the webinar has been completed. So, let us begin. As some of you may know, we've got a few regulars joining us today. My name is Chris Hallum. I am the UK and Ireland manager for UE Systems Europe. My contact details are on this slide in front of you, and you are free to contact me anytime with any questions or any help that you may need. A little bit about UE Systems itself, first of all. So, founded back in 1973, we're a manufacturer of airborne and structure-borne ultrasound instruments, along with software, sensors, and training provider. We are not a service provider. We provide the equipment and the support and training to help you guys be self-sustaining. We are headquartered out of New York. We also have regional headquarters on all continents. And myself here from the UK and Ireland, we come under the European headquarters in the Netherlands, and we have then regional representation around Europe in Germany, France, Spain, Poland, Italy, and Eastern Europe. So let's paint a small picture, first of all, about what we're here for today to discuss. Some of the facts and figures that I will be presenting today are based on the UK numbers, and so for each of the regions, they will be similar. I'm just going to mute all people, please, first of all. Thank you. So these figures are representative of the UK, but of course in each other region, the values could be very similar, could be more, could be less, but you'll be able to find those out. But it's more about understanding the sort of size of the figures as to the importance about what we're talking about today. So let's just make sure this is working. There we go. So yes, some stats back from 2018. Industry in the UK used approximately 22 million tons of oil equivalent in energy, just industry alone. From that, producing approximately 10 million tons of carbon dioxide equivalent in greenhouse emissions. So a lot of carbon dioxide, a lot of greenhouse emissions that are going to the atmosphere that's not great for us. We had the introduction of the Kyoto Protocol, or the Paris Agreement, or the Paris Climate Accords, aimed to help commit to the reduction in greenhouse emissions. And then governments throughout the world, obviously putting pressure on industry as well to obviously commit to energy savings protocols. So where does this mean that ultrasound fits into all of this? Okay, so you're thinking about those sort of numbers of emissions and energy usage throughout the country and industry. 10% of electricity supplied to industry is used just to compress air alone, which equates to over 10 terawatt hours of electricity. It's a hell of a lot of electricity to just compress air. Now, however, on average, as much as 30% of this energy is lost just through leaking systems, which can be equivalent to the entire output of a medium-sized power station. So, for example, according to those statistics that I've researched, there is one medium-sized power station based in the UK just there to feed industry's leaks. In some instances, though, a poorly managed compressed air system can see leakage rates between 30 to 50%. It really much depends on the age and the condition as well. So these figures could be higher. When it comes to ultrasound, the leak application, the use of ultrasound for leak detection is the foundation of ultrasound. It's one of the simplest and earliest applications that ultrasound was utilized for, with the aim of quick, simple gains. So why perform a compressed air survey first of all? Let's have a look at a few factors behind this. So first of all, thinking about safety. These are pressurized systems. It's kind of like a bomb waiting to go off, really. And we need to make sure we're on top of our compressed air system itself, pressurized systems. But we also need to think about flammable gases, maybe, or asphyxiant gases that can prove fatal to human beings if there are leaks out there. So safety is a very important part of performing compressed air surveys or leak detection surveys. Thinking about the environmental impact, thinking about the reduction of carbon emissions if we can improve the energy usage of our systems. Also, quality assurance. A lot of processes are controlled by pressurized systems. And if we have lots of leaks within our system, it's going to affect those processes, reducing maybe the output. And finally, looking at the economic side of it. And I'm going to expand a little bit on the economic side of it because that's normally an area that I get questions about very often. So based on the facts that I said earlier about there being 10 terawatt hours of energy being used just to compress air alone, if we think about on average what industry will pay per kilowatt hour for energy, from my experience and speaking with different industries and sectors across the UK, it normally varies between 8 pence per kilowatt hour up to around 12 pence per kilowatt hour. It could be more, it could be less, depending on your site. But if we just take an average of 10 pence per kilowatt hour for energy in industry, industry would be spending on average approximately £1 billion just to compress air, which is a lot of money. So then if we then take the average, which I would call, say, the lower average of how much compressed air is wasted at 30%, then industry is actually wasting £300 million a year in just compressed air leaks. And that's a lot. So if we think about a well-maintained compressed air system, should be around 5 to 10% of air generated lost to leakage. So that's in a good state. Let's face it, compressed air systems will leak. They will generate leaks at some point. It's always a fighting game to keep on top of them. But if we have 5 to 10% of air lost to leakage, that's a good system. So if industry could meet the top end of this goods figure, you could look at saving industry in general across the UK £200 million a year, potentially, if not potentially more. I think these are quite conservative figures that I've kind of worked out just by taking some of the stats I found in the past. So let's look at the general compressor costs over a 10-year life cycle, for example. And looking at the capital cost to the installation, maintenance, the biggest area that we see of the cost to a compressor over a 10-year life is purely in energy. As we can see here, 73% is in energy costs, but then 30% of this, on average, could be more, is actually wasted. So it's a big area of the cost of a compressor over its life cycle. So how could we save energy across that on our air systems? So there's a few different ways we could look at it, looking at things like better housekeeping, control and maintenance of our compressed air systems, thinking about our air treatment. But another large chunk is talking about fixing our leaks. And if we think about it, this wedge is showing us at about 30%. If we've got 40 to 50% on a poorly maintained system, it's our biggest area. We're looking at fixing leaks as an easy starting point. It's the simplest way to get improvements fast. So let's look at about the principles of behind the use of ultrasound for leak detection. Now, I'm not going to go too detailed in the principles of ultrasound because that has been covered on our previous webinars. And if you've never had a chance to see them, they are on our YouTube channel for you to look back through. But we'll still cover the basic fundamentals here. So we go into a plant or onto a shop floor. They're usually very noisy environments. Audible sound at its source is omnidirectional. It travels through solid objects. It makes it hard to discriminate between what sound is coming from where, if it's relevant, if it's not. Normally we might hear large scale leaks, for example, but we just understand that they're coming from a certain direction, or we have them. Now, we're using ultrasound because we're listening in the frequency range of 20 kilohertz to 100 kilohertz outside of our human hearing range. And this ultrasound is directional, and it doesn't travel through solid objects, which makes it more easily locatable. And sometimes some people ask me, well, what does a leak sound like in ultrasound? Well, a leak in ultrasound sounds like a leak would audibly. What the ultrasound device is doing is enhancing your senses. It's heterodyning and giving you an audible representation of the sound. So a leak will sound just like a leak in the headphones. So ultrasound is generated by turbulent flow. So think about a pressurized system, think about a leak that we have, it's turbulent flow. We'll be using airborne ultrasound, and we'll be inspecting at a frequency of 40 kilohertz. And we'll use a variant different types of modules depending on our access issues, distance issues, and how we can get eyes on and get close to wherever our leaks are coming from. So let's have a look at the methodology used to perform a leak survey on a site. And that methodology is referred to as the gross to fine method. So what we'll do is we'll have a ultrasonic device, either fixed frequency at 40 kilohertz, or we can use a more sophisticated probe and tune it to 40 kilohertz. We'll start with the sensitivity of our probes at maximum level, so we can listen in for the most amount of sound. We'll then start to scan in a gross fashion, and when I mean a gross fashion, it'll be large sweeping motions left and right, up and down, listening for the source of a sound, of a leak. And as we point towards the source of the leak, we hear the increase in sound. As we move away from the leak, we hear a decrease in sound. Kind of like a hot and cold game. So as we start to identify the source of a leak, the sound of a leak, we start to follow that source. We start to move towards it. And as we move towards it, the sound will start to increase. So we start to reduce our sensitivity, focusing in on the source of the sound. As we get closer, our scanning method starts to become finer, smaller sweeps left and right, up and down, pinpointing where we're receiving the sound from. Once we're close enough, we will attach what is called a rubber focusing probe, as you can see in the image below, to over the top of our module to then narrow down and pinpoint the source of the sound, the leak. Once we've identified the source of the leak, we will then move our probe back 15 inches from the tip of our rubber focus probe and take a measurement of the decibel value if we're using a probe that has a decibel readout. So I will now show a short clip about what I've explained there. So that was my colleague Peter Boone there doing a fantastic job of how we would perform the gross to fine method for leak inspection. It's one of the simplest applications to learn to get to grips with. So once we've then identified our leaks, there's a few different follow-up actions that we can take. So depending on the type of equipment that you are using for performing your leak inspection surveys, there are two approaches. So the first of all, we'll be using an analog device. This is one that will just give you a measure of intensity of sound. It's more designed as a troubleshooter. What we will do with this approach is identify our leaks. We will then tag our leaks, and then we will fix them. It's as simple as that. Find it, tag it, fix it. If we have a digital-based device that gives us a digital decibel readout, we can do a few other things. And that's where we will then identify the leak, we will still tag it, but then we will start to look at reporting on it using DMS, our data management software, or the leak application. And then from that, we can create a quantified cost report of all of our leaks. And from there, we can then also supply that report to the workshop, for example, or the mechanical engineers who can then go out and repair those leaks. So going on to reporting side of things, and so if you have a more sophisticated probe with a digital readout and you want to create a report, I'm going to take you through now how we would use that. And that's using the leak survey application, which is a free to download application for Android devices and iPhone devices. It's a very simple way of turning your notebook into a digital notebook. With this, when you first download it, there's a few things that you'll want to change in the settings to make sure that you get the right values when it comes to creating a report. The first thing will be to make sure that you adjust the currency to your region. You'll want to make sure you input how much you're paying per kilowatt hour for energy on site. That's important. Put that into there. You'll also need to then change your state or country, and also put the details in of how often is your compressor systems running. Is it 365 days a year, 24 hours a day, or is it different? And at the bottom there, you can also label your survey name. It could be your plant, it could be a specific region within your plant, or in zones. Once you've done this, you're good to go and get started with doing your leak survey. So as you start performing your leak survey, identifying your leaks, once you've identified a leak, you can then input the decibel value on the probe into this leak app. You can then also put some other things like the location of where you are. You can make some comments on the type of leak that you found. You will then need to check where the leak is, what the pressure at that point of the system is. A common error that I see when people are performing leak surveys is labeling every leak at line pressure. We have lots of different regulators in the system that will drop the pressure down. So we need to make sure that we understand what the pressure is at the point of the system. So I've just had a quick question, someone coming in here asking about using ultrasound on pump inspections for cavitational bearings. Is it also done at 40 kilohertz? No, it's not. It's done at 30 kilohertz. Okay. So once you've then made a point of identifying your decibel value, putting your information in there and the pressure, you can then also select the camera at the bottom to then take a picture of your leak site, where the leak is coming from. That's it then. You then carry on throughout the site, performing your inspections, finding your leaks, inputting the data into the app. It's instead of writing it down on a notepad and then copying it from a notepad onto a computer later on in the day. So once you've then gone through your area or your plant and you've identified all of your leaks, you can then create and generate a report. From here, it will then give you a report file name to produce, so you can put it as a certain zone or your plant, and then click OK, and then you can choose a way in which you send it to yourself. So that can be via email, for example, and then once you've then clicked OK and you've sent the email, you will then receive an email with a file in it that will be a fully costed leak report. And this will take all of the data that you've inputted from the leak app itself, and it will give you a general overview followed by an itemized cost of all the leaks. Now, this is an example here of a leak report that I did on a site in Ireland last year, where we actually did 10 leaks in the space of half an hour on a certain room within the plant. And as you can see from this one, in half an hour, we identified nearly €7,000 worth of leaks in a year. So we can see that it's very expensive, and it's something that you can really easily, once you've identified and fixed them, you can make some severe changes, really beneficial changes. So you get the itemized billing for each leak. It might help you then with actually deciding in what order you might repair them, or if any leak under a certain value, you'll decide, right, we will not do that. We will only focus on ones over a certain value. But you can then highlight in there that you've repaired it, and it'll also show you how much you've avoided by repairing these leaks. Also in the leak report, you'll get the itemized sheets of the leaks that you've taken pictures of. So then you can see where the leak is occurring, the cost of it, and everything else. And that can be really handy when raising work orders when it comes to doing the follow-up action to do the repairs. So the benefits of performing a leak audit itself, it speaks for itself, I hope, at the moment. Reducing energy consumption of our compressor systems, we might start to see that if we start repairing leaks, our standby compressors are not cutting in as much, for example. There's reduced pressure on the system to hold line pressure, excuse the pun there, but it's no longer feeding so many leaks. And there is potential that once we start getting on top of our leaks, if we start reducing our number of leaks by a large percentage, there is potential to be able to reduce the actual line pressure, which again is a win-win situation because we've reduced our number of leaks, which is saving us energy. We start to, and if we have the ability to reduce our line pressure, then we're going to save energy again there. So it's a win-win situation in that respect. If we're doing that, we're going to improve our lifespan of our system, which in turn will improve the reliability. So that's the benefits of it. I hope people can understand and see those are the sort of benefits we can gain from performing leak surveys. But we get a lot of questions about this, but what about other compressed gases? Well, we can report on those too. As you can see, we've already talked about how just using ultrasound for compressed air leak detection, it can save money and it's very expensive, but other gases can come in at an even more expensive cost. And as long as the gas is under pressure, if there's a leak, it's going to create turbulence. If it creates turbulence, we can identify it. So mixed gases itself, so different types of gases, they're going to come to us in different forms, aren't they? Either in canister form, or we're going to receive it in bulk liquid form, depending on the sort of gas we're using and the application. So just a quick question. Someone's quickly jumping in here asking about, are your devices suitable for use in ATEX environments? Yes, they are. There are a selection of probes that are ATEX rated for such instances. And can ultrasound capture air ingress on vacuum systems? You're kind of just jumping ahead of me here, but yes, you can. And I will explain that a bit further down the line today. So I want to look right now at how do we know how much a leak costs us when it comes to bulk liquid gases that we have supplied to us. You would have seen in the report I showed you earlier, there were other costs there associated depending on the type of gas. And with the leak app and with the data management software, we can actually input different types of gases. But what we need to know is how much does it cost us per 1,000 litres of gas? That's what we need to do. And it's normally a common question that we get asked. Because the problem is that most invoices or information that you get on site, depending on the supply of liquid gas, is the units, for example. And we need to work out the 1,000 litres of gas, but we get it in liquid form. So we get this question often, as I said. So what I'm going to do today is go through with you how we work that out. So if you've not got a coffee, make sure you take a sip. If you've got a pad and pen and you like these sort of things, then get ready. I'm an engineer. I love stats and math. So let's get it done. So we've got an example of an invoice here of nitrogen. This is something that I've gathered over my time and experience out there. So I'm using real-time stats here that I got from a case study. So as we can see on this invoice, the liquid nitrogen is supplied in 100 cubic meters. So that's not what we want. So we need to work something out. We've got 2,971 cubic meters. What we do know is 1 cubic meter of liquid is equal to 1,000 liters of gas. So we need to take that 2,971 cubic meters divided by 100 to give us our cubic meters cubed, which we can see here. We do that just in the display there. We then need to understand what our expansion ratio is. Every type of gas will have a different expansion ratio from liquid to gas. In this instance, liquid nitrogen has an expansion ratio of 1 to 696, and that's based at an ambient temperature of 21 degrees C. So a little bit more maths we need to do now. So we've taken our 29.71 meters cubed of our liquid and multiplied it by the expansion ratio of 696, which gives us over 20,000 meters cubed of gas. So now the simple part. So what we do next is we take our cost from our invoice for our gas, divide that by our 20,000 cubic meters of gas, and it gives us our cost per meter cubed of nitrogen. So our nitrogen cost per 1,000 liters is 7.9 pence. Now, depending on the other types of gases, you can use the same principles behind that. So, what about other gases and costs? Well, don't worry, everyone. Don't worry. There's no more maths. I'm not going to do any more of them. We could be here all day if we wanted to do that. So, the prices on different types of gases will vary depending on the grade of the gas, the quantity supplied. What I've got here is of my time doing site visits and helping people out and supporting people. These are some figures that I've got from users out there on different industries and different sites. So these prices and costs are going to be just kind of a reflection of what they are. They will vary depending on what who your supplier is and how much you're getting. But I want to give you an appreciation of the difference. We've said about how compressed air will probably cost between 1 pence or cent to 3 pence or cent per 1,000 litres. So with that in mind, these are the sort of costs for other types of gases. So hydrogen, for example, anywhere between 84 pence to £1.25 per 1,000 litres of gas. Nitrogen, as we've already discussed, about 8 pence. CO2, around 18 pence per 1,000 litres. Oxygen, 21. Argon, 11 pence. And helium, it's quite an expensive commodity, helium, around, it might, £8 to £13 per 1,000 litres. When I worked that figure out, I was quite astonished. But again, it depends on the grade of the helium and also how much of it you're actually storing on site. So just a couple of questions that are coming in. Could you compare identification of leaks with infrared camera gas leaks? So gas cameras are going to use different types of technology in a way to identify the leaks visually. In comparison, what a gas camera is seeing is the turbulent flow of the gas, and that turbulent flow is generating ultrasound. So we can use a gas camera to pick up certain gases, but an ultrasound device will just pick up the turbulence as well. So it'll pick up the leaks very easily. That's the thing. And the level of turbulence can be very low level, and we can still pick it up with ultrasound. So the units cannot be changed. So someone's asked about the leak survey app and the units not being able to change. You have the choice of standard or metric units. So you can change those in the settings, depending on whether it's an iPhone or Android device. So going back to our presentation, as you can see, these are the costs on bulk storage, bulk delivery through tankers. I've given the canister view there. It's just the naming of each of the gases. And hopefully this gives you an appreciation as to the cost behind these gases. So a quick example then of sort of what sort of costs, for example, with nitrogen, we've talked about how I quantified the cost of nitrogen. So if we think about 8 pence per 1,000 litres of gas, a 1.6 millimetre leak of nitrogen at 7 bar pressure could give an approximate annual cost of around £7,727 per year. And that'll be based on the tankers keep coming in and out. And the amount of times that I've had conversations with people on site and they've said, yeah, we kind of have these tankers coming in every few weeks, but we don't really use the gas that much, but we're always getting it filled up. So check your leaks, check for leaks, because it's very, very important. I want to give an example as well on cylinders. I mean, a cylinder, you purchase the cylinder, if there's a leak on it, once it's gone, it's gone. It's not going to be really an annual cost as such we're looking at here, but we could look at it in the length of time it would take for that gas bottle to maybe empty itself. So I've given a little example here of an argon industrial grade cylinder, 11.01 meters cubed, with a 2-bar regulator on top of that. If we have a 5 decibel leak on the top of this regulator, for example, very, very small, that leak will empty the canister in 6 days. So it's really, really important to check your gases as well. Those are areas where you can make savings on your site. Another question, can your device be used to determine control valve leak rate? If we're looking at internal leakage, no. But if we've got external leakage, for example, and we know the pressure of the system, then yes, we can quantify the leak rate on that. We can give you a guide with that in the report. A leak report will provide the cost per year. It'll also give you a defined leak rate as well. But that's only on external leakage. If we're looking, for example, control valves with internal leakage, all we can do with ultrasound in this format is determine whether it's leaking or not. So, thinking about quality assurance then, and alternative leak applications using ultrasound. The device ultrasound can be used for things like hatch testing. We see this in the marine industry, for example. This is where we're not necessarily pressurized, but if people understand how ultrasound works, ultrasound does not penetrate a solid object. So you could place a ultrasonic tone generator on the one side of the actual hatch with it sealed up. If there is an air gap, we will hear the sound. So we can check for the quality of hatches, for water tightness, for example. We could also use a device to check for vacuum leaks. So vacuum leaks still produce turbulent flow. Now, the turbulent flow, instead of being external to the pipework, it will be internal to the pipework. So the level of ultrasonic emission will be a bit lower, but what we would do is we would be a bit closer to those assets to then determine where the sound is coming from. It will still produce a similar sound as a standard pressurized leak. We could do this on vessels. We could also do it on enclosures where it should be airtight, for example. So we could even put a tone generator inside of these assets, and if it's perfectly sealed, we would then not hear that tone generator. But if there's any type of air gap, we will hear the tone generator, and because the ultrasound is directional, we will pick that up. And also such things as wind noise and water leak testing as a quality assurance approach as well. It's still using the device for leak detection to check for the quality of seals, maybe on doors and windows and things like that. So there's many different things when we talk about leak detection and how we can use ultrasound for it. So in conclusion to today's webinar, compressed air, I would like to think you could all agree with me here, is air is not free. Compressed air is not free. It's actually quite expensive. Other types of gases are equally as expensive, if not even more expensive. We can see this sort of technology can be seen as one of the quick wins, leak auditing, economically and environmentally. A lot of companies now corporately will have some sort of commitment to reductions of their carbon emissions on sites. And this is a quick and easy way to add to those targets. And for example, one large leak, if you're struggling to get the justification for this, one large leak alone would pay for an ultrasound device just to do this. It's very straightforward. Like I was saying, leak detection is one of the easiest applications when it comes to ultrasound use. And using the right equipment and training with the right reporting applications will help you prove the cost savings that are there for you. And one last thing I do want to say is a leak report, if you complete it, will not save you money. It's you and your team fixing the leaks. Fixing the leaks will save you money. I'd like to thank you for your time today, everybody. This is a little bit of a shorter webinar than some of our other ones, but as we can see, it's equally as important as the other applications, and it's one of the easiest and quickest ways to get quick, fast wins on site. If we have any questions, please feel free to put them through to me on the chat group right now. I will answer a few questions now, and then what I will do is you can contact us on my contact details on the screen in front of you. You can go to our website where there is a learning center that talks about all the types of different probes and what you can actually do with them. And this will be uploaded onto our YouTube channel. Can we use this device? So a couple of questions coming in. I'm going to answer them now. So can we use this device for refrigerant leaks in HVAC? As long as anything is pressurized, if there is a leak, we're going to detect it with ultrasound. I've done it on as simple refrigerant leaks on a small cooperative store, for example, checking for leaks in their systems. During vacuum testing with ultrasound, how readings will vary. So with vacuum leaks with ultrasound is more about identifying the leak. With ultrasound, we cannot quantify a vacuum leak, we can just identify it. So with will the decibel values go down then with vacuum leaks? No, the decibel value will be dependent on the size of the leak. It can also be dependent on the shape and size of the orifice as well. The leak site will also give a dependence on the decibel value. The more turbulence there is, the more higher the decibel will be. But the simple thing with ultrasound and vacuum checking is as you point towards it, you'll hear it, and as you move away, you'll lose it. So you can pinpoint exactly where it comes from. So a quick question about the nitrogen the nitrogen example that I gave. That was just using some of the statistics and data that I have previously of the size of a leak and the cost. What you would do in the app, for example, is that you would put in the cost of nitrogen in there, and then from that you'll get a decibel value, and that will also give you a cost of the leak. The next webinar, which is part 2 of energy conservation, using ultrasound to improve your steam system, will be from 2 weeks today. I will put out an announcement on that tomorrow, and mailings will go out advertising the next webinar. So I think we'll call that a day. We'll call that a wrap for now, guys. Please feel free, if you have any other questions, email me, get in touch with me anytime. We're always here to help.